Hey Matrix, welcome back to the next video in the chemistry playlist. Today we're looking at question 6 of the 2020 November chemistry past paper. If you don't have the paper, there's a link in the description below where you can download the paper as well as the memo. And once you have the question, then we can continue with the video. Okay, let's get started with question 6. So question 6 is looking at the reaction of iodine. So we've got I2 gas, which then breaks up into 2I gas. Okay, they've given us here that it's a equilibrium equation or question that we're dealing with. They've given us the temperature at which it takes place, and then they've given us our Kc value. Okay, so 6.1 is just a definition for reversible reactions. So you can go look at your list of definitions and write that down. I'm going to be focusing from 6.2 to 6.5. Okay, so 6.2 says at equilibrium the pressure of the system is increased by decreasing the volume of the container at constant temperature. Okay, the important part here is constant temperature. Then they ask us what will happen to the following: state increasing, decreasing, or remain the same. Okay, so 6.2.1 says the value of the equilibrium constant. Okay, now remember the equilibrium constant is K. Okay, that's your Kc value, which is your products over reactants. Now, the only thing that can affect the Kc value is temperature. But because they've told us that temperature is constant, okay, we can see that the Kc value, regardless of the change in pressure and volume, will remain the same. Okay, now 6.2 says the number of moles of I2. Okay, so the left-hand side, what's happening to the number of moles? Okay, well, let's have a look here. So initially we had a volume of this amount over here. Okay, then we've decreased the volume by to increase the pressure. Okay, but remember temperature is still constant. Okay, now what is going to happen to the moles of I2? Okay, well, I've decreased my volume in order to create a greater pressure, which means there's less space. Okay, so now we've got to consider which molecule, or are we going to have more molecules or we're going to have more atoms? In this case, to take up less space, we're going to produce molecules. Okay, so in this case, I2, okay, is going to increase in moles. Okay, so it says the number of molecules, sorry, so we'll have an increase in the molecules. Okay, now 6.3 says explain question 6.2.2 with referring to Le Chatelier's principle. Okay, now remember Le Chatelier's principle states that if there's a disturbance in equilibrium in a system, the system will change accordingly to reach equilibrium again. Okay, so I've got these 5 steps we can follow when talking about Le Chatelier's principle. So we look at the change of the system, we then define the Chateliers principle, we look at the system's reaction, we consider which reaction is favored, and then we discuss the results. Okay, so because we've increased the pressure, and decreased the volume, okay, the change in the system, okay, is going to be an increase in pressure. So the first thing I'm going to state is that there's an increase in pressure. Okay, this is number 1. Okay, then by Le Chatelier's principle, okay, the system adjusts to minimize the disturbance. Okay, to minimize disturbance. Okay, that's number 2. Okay, so then what do we look at next? We look at how the system reacts. Okay, so the system will favor the reaction that produces the smallest amount of molecules. So adjust to form least amount of molecules. Okay, why? Because I have a smaller volume, so I'm trying to pack in as much as I can, or now the molecules have to rearrange in order to for everything to fit into that volume. Okay, so therefore we're looking what will give us the least amount in this case, okay? And then that is by 3. Okay, now we need to see which reaction is favored. Okay, so we can see that the reverse reaction, okay, why? Because here we have 2I, okay, but if we reverse it, then we produce I2, which is a smaller molecule than having just 2I atoms or iodine atoms. Okay, so then the reverse reaction is favored. Okay, and because the reverse reaction is favored, new equilibrium is reached. Okay, that's 4, and then new equilibrium. Okay, so it is quite a bit for 2 marks, but this is the best approach you can take for answering Le Chatelier's principle. Okay, now 6.4 says at 227 degrees Celsius, the Kc value of the reaction above is 5.6. So we can see there's a change in the Kc value. Okay, then they ask, is the forward reaction endothermic or exothermic? Okay, so initially we had 727 degrees Celsius and a Kc value of 3.76 times 10 to the negative 3. Then there was a decrease in temperature, okay, which means it's now at 227 and my Kc value has decreased as well. Okay, so let's have a look here at what's happened to the Kc value, because then it asks, is it endothermic or exothermic? Okay, so we can see that my Kc value is decreased, okay, and if that happens, my reactants must increase and my products must decrease. Okay, that's just rules of fractions. Okay, so because there's an increase in products, okay, this means the reverse reaction is favored, okay, because my products my reactants have increased, not my products, my reactants, which means the reverse reaction's favored, okay, and then we can see that there's also a decrease in temperature, which means the reverse reaction is exothermic. Okay, therefore we can state that the forward reaction is endothermic. Okay, because if I wanted to go back to where I was, I have to favor the forward reaction, therefore I need to put energy into the system, and therefore it's endothermic. Okay, now let's have a look at question 6.5. So 6.5 is your equilibrium calculation. It's worth 9 marks. It's quite a lot. Okay, so for this, I'm going to do it on a separate piece of paper. Okay, so everything that's given over here, I've indicated over here. And what it's asking is calculate the initial mass of iodine molecules in the flask. Okay, so they've given us initial volume, they've given us the temperature, the Kc value, and they've told us we're dealing with I2. Okay, but now we need to find the initial mass. Okay, so we're going to use our Rice tables. Okay, so I've written out the equation over here. I've done my ratios to make sure the equation's balanced. Okay, now what we need is our initial moles, that's X. Okay, and remember, when we talk about initial moles, the reaction hasn't taken place yet. So this is always 0 unless stated otherwise. Okay, now we need to find all these changes over here. Okay, but what they've given us is they've given us the Kc value, okay, and we have the concentration over here at equilibrium, okay. This is the concentration of I2. So we can use our Kc formula. So Kc equals to my products, okay, all over my reactants. Okay, so I have my Kc value, I can substitute that in, okay, and I can work out what my reactance is, because that's what we need here in order to work backwards. So my reactance is then, okay, going to equal to my products. Okay, now remember, it's 2 moles of my product, so I have to square this bracket all over my Kc value. Okay, so if you substitute everything in over here, we are then going to have 4.7, okay, 9 times 10 to the negative 3, okay, that's all squared over my Kc value, which is 3.76 times 10 to the negative 3, okay, and if you work that out, you should get a value of 6.102 times 10 to the negative 3, okay, remember that's moles per decimeter cubed because that's my concentration. Now I have this concentration for I2, so I can fill that in. 6.102 times 10 to the negative 3. We have this one as well, that's 4.79 times 10 to the negative 3. Okay, now I need to work backwards. Okay, so in order to get the next value, okay, up here, I need to times everything by the volume that was given. Remember, to get n on its own, n is going to equal to c times v. So if I times this by 12.3 decimeters, okay, I'm going to get the following. This will be 0.0295, and this one over here will be 0.0589. Okay, that was by timesing this by 12.3. Okay, now I need to work out the change. Okay, so the change is going to come in over here. The change is going to be the same. Why? Because my ratio, or I'm going from 0 to whatever this amount is, so this amount will just be here. So this is 0.589. Okay, then I use my molar ratio over here. Okay, so it's 2 to 1, so I need to divide this by 2 to get that. Okay, so if I do that, oh, I have the wrong value here, my bad. This should, be 0.0751. Okay, if I times this by 12.3. Now, I work out with the ratio to get this over here, so I divide this by 2, okay, which means I'm going to get 0.0295 over here. Okay, now in order to get x, remember the change, okay, so the change was x minus the 0.0295 gives me 0.0751. Okay, now I need x, so I add these two together by taking this over. So x is then going to equal to 0.1046 moles. Okay, remember all of this here is in moles. Okay, now that I have that, I can work out the mass. How do I do that? Mass equals n moles times molar mass. Okay, and what is my molar mass? If you're going to work that out, or if you're going to check the periodic table, you should get 254, and this is what we had up or over here. Okay, so this is going to go over there, so that's 0.1046. Okay, and if I plug that into the calculator, you should get 26.543 grams. Okay, so for this question, we had to work from Kc back to initial condition in order to get 26.543 grams. Okay, and that's how we go about doing this question. Okay, if you found today's video helpful, then please leave a thumbs up on the video. If you have any questions about question 6, please leave them in the comment section down below. I'll get back to them as soon as I can. Please go check out the channel as well. There's physics and maths past paper questions done as well. While you're there, please consider subscribing to the channel. And remember, it's never too late to have an OIC moment.